All right, let's start. Thanks for being here. I'm really glad to be at Sensor and Test. It's my first time here, and yeah, we'll talk about today a new class of sensors that Melexis has introduced for cutting-edge inductive position sensing. We talk about sensors featuring on-chip digital signal processing with very, very nice performance, especially with zero delay and very high accuracy. So I will first introduce to you the inductive technology for position sensing, how it works, which kind of motions we can sense, which kind of applications we can target. And then I will actually show you our portfolio, and we will go in the depth of the IC, how it functions and why they behave like they behave, and then we will conclude. So let's start with the first part, inductive position sensing. Say what we talk about. So an inductive sensor is often looks like that. We have actually a PCB, the green part here, where we have printed a set of coils. We will see their functioning just in the next slide. This is the transducer, so the one that generates the signal that carries the information on the position. There is a moving metallic object, the target, just a metal, nothing else. A conductive metal is sufficient. And this object is there to modulate the inductive coupling in between the different coils of the transducer. So to generate induced signals whose relative intensity vary over the movement of the target. And finally, we have an interface IC that is there to drive the transmission coil and to capture the signals of the receiver coils and to elaborate the position of the movable object, which is the one that is attached to the piece we want to sense the motion. And so one could ask himself, why going inductive? Why not staying on magnetic sensors or on more classical sensors? Actually, the main reasons is that inductive sensing is completely stray-field immune. There is really no issue from external magnetic fields caused, for example, by current wires or big permanent magnets, for example, if you are inside the motor. We work actually in a very narrow frequency band in the megahertz range, so we are not at all disturbed by magnets, by PWM signals of a motor, etc. It's also a very, very accurate technology because everything is determined in the end by the geometry of the coils and of the target and in their relative position, and these things change very little over temperature. We're not relying on the properties of a semiconductor that change very strongly over temperature, for example, or over stress. And so that is a key factor to have a very, very stable and very, very good accuracy. And then the sensor itself can be made very immune to mechanical misalignments if done well. Another key aspect is that the transducer is on the PCB, so it's not integrated in the chip. So every time you do a new sensor, you can tailor your transducer. You can make it really fitting the stroke you want to sense, the diameter of your object, the number of pole pairs of your motor, and these allow you to really always and constantly take the best out of your application. It's also very reliable technology. We have a very, very long track record already in the automotive industry, where the technology is used since more than 20 years, and we have already hundreds of millions of chips in the field. So we know that it is reliable and safe. And talking about safety, with the current trend, especially in the automotive market, to have more and more safety requirements, especially for the by-wire application where we are requested to go AZD fail operational, we can co-integrate actually a magnetic and an inductive sensor together. They are completely orthogonal, they do not interact with each other, and so we can really achieve a true heterogeneous redundancy, which is very, very beneficial for the defense of a safety case. So now that we know a bit the big lines, let's see how the transducer itself works. So we said we have a set of coils on the PCB. There are two types of them. There is a first coil, the transmission coil, this round one, which is there in order to generate an AC magnetic field. So this is a coil that is actively driven by the AC, by an AC voltage. And this primary AC field is there to excite eddy currents in the conductive target. These eddy currents, in turn, generate a secondary field that is then selectively picked up by the receiver coils, which are designed in a way to just couple to the target and not to the TX coil. And as you move the target, as you rotate it, the coupling to one or the other receiver coil changes, and you have different signal levels in the receiver coils so that you can elaborate a position. To make it a bit more visual, you can see here an illustration, a little movie of how the sensor works. So you see the target rotating on top of the PCB coils, and you can see how the magnetic field looks like in the coils plane. So the Z component. You see this cross of low field. That's where the eddy currents of the target screen out the magnetic field of the TX coil. And you can recognize then a movable pattern that rotates together with the target. And you see on the right the amplitude of the signals generated in the receiver coils that is modulated sinusoidally. And as we have three coils staggered by 120 electrical degree, one with respect to each other, we can retrieve a three-phase signal set that can tell us the position. So now you could ask yourself, why did we choose to go three-phase and not to just have a sine-cosine simple system? Actually, there is a very good reason for that. And it has to do with the fact that no physical law imposed to these signals to be sinusoidal. They could actually be, they are actually always a bit distorted because you see that the magnetic field pattern here is not a perfect sine. And if you have a sine-cosine signal set, then you cannot do anything against that. You will need to live with your errors coming from the signal nonlinearities, or you will need to work very, very hard in order to optimize the coil geometry and the target geometry in order to remove as much as possible this inaccuracy. But actually, when you are in a three-phase coil set, given that you will do a Clark transformation in between the moment you receive the signals and the moment you elaborate an angle, this Clark transformation is able to reduce greatly this inaccuracy because we can filter out the biggest error contributors. And yeah, you can see it illustrated in this slide where we compare a quadrature and a three-phase coil set in terms of performance. We see that in a quadrature system we have a relatively large fourth harmonic error. That's something you can really check in the literature. If you search, you will really see these kind of errors in these systems. It is due to the fact that the signals, the receiver signals, are a bit saturated, and they contain a third harmonic. And this third harmonic is completely removed by the Clark transformation, and in a three-phase system, we have a much, much lower error. So even without any complicated coil optimization or system optimization step, we can really have very, very nice performance, and that's extremely beneficial, especially when you have short development cycles, but also when you have to work with very small sensors, because there the traces are very dense, and you have much less freedom to perform optimizations. All right, so that's our approach. With that, what can we sense? So we can actually have a lot of options of motions to sense. Let's start with the rotary motions. There we have mainly three categories of sensors. The first one are the rotary O-shaped. We call them O-shaped because the coil set has the shape of an O, of a circle that surrounds fully the target. So all the target lobes always superposed with the coil set. It's a very, very nice configuration because this approach allows you to have an averaging effect that remove the great majority of the errors coming from misalignment. So you can actually build sensors that are extremely robust against assembly inaccuracy. The next category are the rotary C-shaped sensors. So they are, let's say, the cousins of the rotary ones. They are just, let's say, cheaper because the PCB is smaller, but we do not anymore cover the full coil set. Sorry, the full circle. So we do not overlap with all the target lobes, and therefore we are more exposed to effects of misalignments or of target manufacturing inaccuracy. But they are the solution to go for if you have a very, very big, for example, a big motor with a big shaft where you have to stay around it. It allows to keep you the cost to reasonable levels. And finally, we have the arc motion. The main difference between this and that is that in this configuration, the target can move continuously over multiple periods. Here we just have a limited angular stroke. That could be the case, for example, of a pedal or of a knob. And here again, we have a coil set that just covers the stroke. Okay. So the kind of applications that we mainly look for and that where we are already pretty successful at are motor position sensor, pedals, actuators of any sort, hand throttles in electric vehicles, human-machine interface controls, etc., etc. And then beside the rotary sensors, as you can imagine, we have the linear sensors, so sensing of the linear motion. In the end, we have here a straight PCB where the coils is stretched in order to cover the stroke of the metallic object that moves. And also here we have a lot of freedom in terms of design. We can design sensors for very, very small strokes, down to 5 or 3 millimeters in a full package space of less than 2.5, 3 centimeter. Or we can go very, very long. There is, let's say, theoretically no limits. Then in practice, we see a limit around 30 centimeter. And there we can actually cover motions that are very, very important, that would be very difficult to cover with other technologies, like, for example, magnetic sensors. You would need a lot of sensors along the stroke in order to cover that. There you just do it with a single IC. And so here again, where do we find the linear movement? In pedals, steering rack sensors, actuator sensors as well, big suspensions for trucks, for example, industrial controls. There are many, many occasions where you can be in the need of sensing either a small or a long stroke. And finally, the last point I want to make about the technology itself is about redundant design. So we discussed just before about safety and high safety standards. This implies often the use of redundancy. And one can ask himself, will this require doubling my PCB space? So fortunately, the answer is absolutely no. We can actually intertwine together two coil sets in order to really have the same footprint of a non-redundant design. So we don't have to pay a premium in terms of space for a redundant system. We can actually co-integrate the two sensors together and have a very, very compact design as well. Okay, so this was to cover the basics of the technology and what can be done. So this prepares the ground to introduce our chips. So our portfolio of inductive sensors, which has two main elements today, the MLX 90510 and the MLX 90513. So the first one is an inductive resolver, meaning it has a sine-cosine differential output. It is a very peculiar resolver, and we will see the details in the next slide, because it is based on a digital core that computes on chip the angle and compensates its inaccuracies, and then synthesizes the sine-cosine outputs in order to provide signals with high strength and stability. It is really a perfect sensor for motor applications, and as we have seen just before, we can cover end of shaft, through shaft, or side of shaft topologies with all their advantages and disadvantages that we just discussed. The second member of the family is the 90513. It's an inductive position sensor, so the output is not anymore a sine-cosine, it's a single pin that can provide either an analog ratiometric or a PWM or a cent or an SPC output. There is a very great deal of configurability that we have in this chip. It is also a chip that has the best-in-class capability of handling small signals, so it can work with very, very, very small designs, which is often a requirement if you want to fit in space constraints applications. And it's very safe in the sense that it is AZC for all output modes. It's the first sensor that Melexis does, which is AZC in analog ratiometric mode, for example. Very flexible, very capable, very performing, and able to cover all the motions as well, because these are defined by the coil set you touched. So Digging a bit deeper into the 90510, I think we really need to, in order to understand the chip, we really need to go to the block diagram and see how it works inside. We have actually three main parts. We have an analog front end whose function is to excite the transmission coil via the oscillator that works with a resonant tank constituted by capacitors and the transmission coil itself. And then we have the signals that come inside the chip that needs to be filtered to remove high frequency disturbances, differentially amplified, to remove the common mode, so to do the first step of the Clark transformation. And then we have a baseband conversion step, a final amplification, and then the signals are fed to the ADC. So we are not just generating at the output an analog process signal, but we really go into the digital domain. And why do we do that? Well, because we can do a lot of stuff in digital. First of all, we can do an offset compensation, so we can program values of offset in the chip to be removed from the input signals. And then we calculate an angle. We don't just do it with a traditional arc-tangent operation. That would not be fast enough. We rather do it with a tracking loop that at the same time does not just calculate the position, but also the speed and the acceleration of the rotor. So with this information that we have available inside the chip, we can also perform a propagation delay compensation and a compensation for acceleration effects that come with a second-order system like a tracking loop. So this means that the output of the chips is really an instantaneous representation of the position of the rotor without any delay at all. And even if you have acceleration phases in your, for example, in your motor, this will not impact at all the accuracy on the output. The tracking loop also includes a linearization feature, so you can actually program a 16-point linearization curve that can be used to counteract inaccuracies of the sensor coming from coil non-idealities or from mechanical tolerances. And as we have a digital angle available, we can also just simply do additions to that. So we have a mean to electronically control the position where the sensor will provide a zero output, which is very, very nice when you have to do your alignment, when you mount your sensor, your resolver inside the motor. You don't have to do any kind of mechanical adjustment or difficult step in order to find where is the zero. You can just program to the sensor, okay, at this position I want zero output, and it will be achieved. So once we have a digital angle compensated, corrected, etc., we just synthesize a sine cosine value, and we then provide the analog output on the analog backend. With this approach, the advantage that we have is that we are not at all dependent on the input signal strength for the output signal strength. So whatever the input signal level we have at the input side, the output will always be strong. You will not see any kind of AGC effect that will provoke your signals to have steps in terms of amplitude. And secondly, we synthesize all the signals from regulated voltages, so any kind of disturbance on the supply will not be transferred to the output. So this gives a very, very good EMC robustness. And so I think that we can now understand here the points that we have on the right. So all these measures that we have on chip allow us to reach very, very good accuracies of less than 1 electrical degree for a full system. And the AC itself contributing with only 0.36 degrees up to the highest speed. And this error includes noise, propagation delay effects, etc., etc. The signals are extremely strong and independent from effects on the input. We have an extremely good latency of only plus minus 120 nanoseconds in worst case. We have acceleration compensation, 16-point linearization, and the zero programmable position. So which are the applications that we target with this chip? In the automotive space, as you can imagine, everywhere where there is a motor, especially powerful motors, that can generate stray fields that are subject to strong PWM driving signals, that have large permanent magnets inside that can very easily disrupt the functioning of a magnetic sensor. So traction motors, brake boosters, electric power steering, everywhere you need high performance and high precision, an inductive resolver would be really the best choice. But automotive is not just our playground. I list here some non-automotive applications. For example, again, resolvers for two-wheeler motors. That's something where we really see a very, very good fit, or encoders in robotics and industrial systems. All right. But then, I mean, there is no limit to fantasy. We can actually, let's say, wherever you have to sense a rotation and you want a sine cosine output, the 90510 is the right solution. So I think now it will be much easier to also understand the 90513, which is in the end based on a very, very similar architecture. We find back the same analog front end that we have seen in the 90510 that has been optimized to really handle very, very small signals. The digital block is also functioning in the same way. It just has a bit more linearization points to handle, say, a bit more difficult nonlinearities, especially in linear sensors. What is very different is the backend, which is not anymore a sine cosine type, but it's a single pin output that actually provides, based on what you program in the chip, an analog ratiometric signal, so something that goes from 0 to 5 volt depending on the position, or a PWM signal, or a center or an SPC. We for sure benefit from the low latency of the architecture, so we also have a sub-microsecond latency for this part as well. And I think one also of the key features of the AC is that it is extremely flexible in terms of signal of output frame format. We support all the CENT, all the SPC frame formats, and we have also the freedom to change the tick time and to reduce it from the standard 3 microsecond down to 1.5, 1, or 0.5 microsecond. So we can have a very, very fast refresh rate at the output, even if you are doing these digital outputs up to 10 kilohertz. So this makes the chip suitable also for some motor application where you just use one wire in the end instead of 4, if the refresh rate is sufficient. And here, let's say the applications are the same. The ones in the automotive space that we have listed a bit at the beginning of the presentation. Pedals are an extremely good fit. Steering angle sensors, where we have two rotary units that need to be sensed. You can also do combined magnetic and inductive steering angle sensors. That's very nice. And actuators, where the actuator could actually result in whatever kind of motion. We can always make a coil set that fits to that motion. Outside automotive, examples are hand throttles in e-mobility, human-machine interface controls like buttons, joysticks, knobs to turn. All these as a very good fit. And then again, there is no limit to what we can do. As far as you need a movement to be sensed, we will have for sure a solution. So that was a bit what I wanted to show you. Going now to the conclusion, I hope I could really convince you that inductive position sensing is a flexible technology that can be adapted to a very great deal of applications. And the Melexis MLX 90510 and 90513 offer a very unique in the market digital-based sensing platform, which is characterized by a very, very high accuracy, a sub-microsecond latency, and a complete output protocol portfolio. So thank you for your attention and for having been here. Any question on your side? Slide number 3, okay. This one? You can actually, if you want, actually, we have a paper on our website that you can freely download where everything is explained. You will actually find a very, very in-depth explanation of why we are better in terms of accuracy with three-phase. So I really advise you to go to our website and gather this material because, yeah, it allows you to really understand the details. And for sure, do not hesitate. The datasheet of these chips are on the net as well. So just go there and take a look. And do not forget also, we have a demo at the DACOM West booth where you can actually try the MLX 90513. You can see physically how the different sensing modes look like. And so you can really have an idea of how it works and how it looks like. Yes. Thank you.